and welcome back to the Extremely Open Science recap video. So we're just going to quickly recap what we've been doing and then specifically what we did last week. So we've been trying to work with simulated genomes. When we took just a handful of genomes, the big stars of microbiology, coli, etc. We introduce mutations, and then we check how big their genes are, and ideally doing this in a smart way by doing it within each k-orthologous group. So in the previous week we had cleaned up the code and made it a little bit more scalable so it doesn't save as many intermediate files. But this week or last week, I spent actually a lot of time consolidating and cleaning up what we've done in the past, and part of that was to be able to run it at a larger scale. And so one of the things we did was just very, very technical, but we converted to using pixi. So instead of using conda, we're switching over to pixi. I'm also switching some of my other projects internally to use pixi. It's just significantly faster. So let me just show you. For example, I can run a lot of things using the run command. For example, environments. For example, like this. And this is something that works, and I can do the conda version as well. But in conda, it's always a little bit slow. It adds, several seconds of, or like a second and a half of overhead there. So we switched over to using pixi, which means we created this pixi.2ml file. We specified all our dependencies. We spent a little bit of time figuring out how to get checkm2 to work. In the meanwhile, I've actually talked to Alex, who's the author of checkm2. He said that in the meanwhile, this issue is fixed. So, but last Tuesday morning, we still have to ensure that we're using checkm 1.0.1, and then we specified all our dependencies here, and so that was going ahead a little bit too much. Our dependencies here, and then we can run things like this: pixi shell environment sardine, and then we and then we cleaned up the code, and we started to run our simulate code, which we added back these special case files. So whereas before, we started with only these special ones, then we said, okay, let's get a random sample, and last week said, okay, we use the random sample plus this one. So we wrote code here. Actually, I made a mistake, or I incorrectly accepted a bad suggestion from GitHub Copilot, where there was a very silly typo here, and then so nothing actually ran afterwards. So I'm just gonna fix it now. So this I want to return. What I want to return is the file list, and not every. This was just basically Copilot got the wrong variable. So this was complete nonsense. And once I actually ran it, it did return complete nonsense. So return file names from. Okay. So I'm going to fix that right now. And then this week's I actually cheated. I cheated because instead of running things on my laptop, which was one of the things I said I would do, this was taking a little bit too long, so I just actually threw it on the cluster and ran everything in a few hours. And I will actually, for tomorrow, even run a little bit more data. I've been trying to figure out if there's a way of doing this and making all of the intermediate files public or at least accessible. But maybe on stream tomorrow we can talk about it. But let me show you what it looks like. So this is here. I did this just before coming on. So this is now couple hundred lines. Again, x-axis is the number of mutations, and here each line is a genome, and then the dashed lines represent the the zero. So ideally we wouldn't have these ones here. So these ones here that start, this sum of z scores below -4. This is this attempt of getting a metric, and so ideally this metric would very clearly separate the good guys from the mutated ones. So, but some of these here are outliers. We also explored a little bit during the stream what was going on with some of these stranger ones. So tomorrow I'm going to try something completely different, or I'm going to try something which is, let's switch away from using this KO annotation and try eggnog mapper. So we'll probably during the stream write the code to do all of that. There's probably again a lot of computation. I'll try to be a bit smarter about it, because one of the issues is that when we go through this, increase the number of mutations, there's actually a lot of repetitions, because when we have say 25 mutations, very few of the genes are actually mutated. So we're doing all of this computation on essentially copies and copies of the same thing. So we'll see tomorrow. Maybe we'll write a little bit of code to be a little bit smarter, to avoid the duplication, so that we can keep scaling this up, and hopefully get a bit better result. Anyway, this is it's not terrible. I mean, it's not terrible. I mean, and as I said before, it's very unlikely that this would be the final version of our metric. It was something, we could potentially improve it, clean it up. We could look at some of the KOs are potentially more likely to be unstable. But if still, this would potentially lead us to a few false positives. These genomes here would be marked as, oh, these are not very good based on this metric, because they look much more like a genome with a lot of mutations than they look like a high quality genome. Could also be that these are genomes with a lot of mutations. Could be. But anyway, let's continue tomorrow. So far we're making progress. There's some I'm gonna push to GitHub this bug fix. So every GitHub, and we subscribe to the channel. I'll be posting a few other things on the channel as well. I'm not just about extremely open science. I'm going to try to post some things in the near future. All right. So I am also going to be trying to start the music here. I am also going to be streaming tomorrow. So see you there, and talk to you soon.